In this video, I'll discuss how to use the chain rule, or as I prefer to call it, the composition rule, because it involves finding derivatives when functions are composed with other functions. So for our very first example, let me illustrate what I mean by a function composed with another function. If we wanted to find the derivative of y equals sine of x, that would be easy, because we've already probably memorized that sine's derivative is cosine. But what if instead of x as the input of sine, we put something else? Let's start with something simple, like 2x. The derivative of sine of x is cosine of x. But is the derivative of sine of 2x simply cosine of 2x? Let's investigate. Looking at a graph of sine of 2x, and estimating the slope of the tangent line at a few points, we can get a good idea what its derivative should be. For example, at x equals 0, if I'm trying to estimate the slope of this line, I might draw this tangent line. At x equals pi over 4, I draw a horizontal tangent. At x equals pi over 2, I draw a steep negative tangent. At 3 pi over 4, I draw another horizontal tangent. And at pi, maybe another steep positive tangent. Now the question is, about how steep are those tangent lines that I was drawing at 0, at pi over 2, and at pi? Do they appear to have a slope of 1 and negative 1, like regular sine x would? Or instead, does the slope look a little steeper? If we focus on that first tangent line that I drew, it seems perfectly reasonable that that might have a slope of 2 rather than 1. So if I plot a 2 here, I get a sense of what sine of 2x's derivative would be at 0. Meanwhile, at pi over 4, I can see a horizontal tangent, so I'll plot a 0. At pi over 2, it looks like the negative equivalent of the slope at 0, so I'll plot a negative 2. And then I'll plot another 0, and then another positive 2. And when I play the game of connect the dots, what I'm looking at here is not a graph of cosine of 2x. It's a graph of 2 cosine of 2x. So that's the question. Why is the derivative of sine of 2x not just cosine of 2x, but instead it's 2 cosine of 2x? Where does that extra 2, that change in amplitude, come from? Well, once I state the chain rule, I think it'll be perfectly clear. The chain rule says that if you want to find the derivative of a function f, which is composed with another function g of x is plugged into f, then you must take the derivative of f and leave the inside function alone, and then multiply by the derivative of the inside function. That's how the chain rule works. And so if I want to take the derivative of a function like sine of 2x rather than just sine of x, the chain rule is telling me take the derivative of sine, that's cosine, but leave the inside function there. Leave the 2x where it is, and then to complete the problem, multiply by the derivative of the inside function, and the derivative of 2x is where that extra 2 comes from. Keep in mind that cosine of 2x times 2 is not cosine of 4x. You don't want to mix up that 2 in the argument there, so we typically rewrite this as 2 cosine of 2x. There is a strategy that I use in order to know when to use the chain rule, and I think it'll be kind of familiar to you. Think back over the course of the year and think of all the times that we had to use a happy face or some other use substitution in order to solve a problem and make it simpler. Keep your eye out for those types of situations. Think about all the different functions that we used over the course of the year. We learned about the squaring function, x squared. Well, if something else is being squared, like a binomial, 2x minus 1, then the chain rule is necessary. Think about log functions, natural log maybe. If there's something other than just x inside the natural log, then the chain rule will be necessary. That also goes for square roots, trig functions, and even exponential functions. E raised to something other than x is going to need the chain rule. which of course reminds me of how I learned the chain rule back when I was in high school. If I need to take of f of something other than x, then the rule says to take the derivative of f, but don't touch the, and then when you're done, don't forget to clean up the poop. Let's see an actual example. If you were asked to find the derivative of y equals the quantity 2x plus 1 to the fourth, you could proceed by using the binomial theorem to expand 2x plus 1 to the fourth power, and then take the derivative of each individual term using the power rule. However, the chain rule gives us an easier way. The derivative of 2x plus 1 to the fourth power is going to be equal to 4 times 2x plus 1 to the third power. And then don't forget to clean up the poop, and that is multiply by the derivative of 2x plus 1, which is 2. And thus, the derivative of 2x plus 1 to the fourth power would simplify to 8 times 2x plus 1 to the third power. And at that point, you could decide whether you wanted to expand 2x plus 1 to the third power using the binomial theorem, or just leave it as is. Let's look at another example. Say you want to find the derivative of y equals e to the x squared minus 9 power. This is a job for the chain rule. And that's because it's not just e to the x, but e to some other function. So what I'm seeing is x squared plus 9 is the inner function. This is the one that must be left alone and then cleaned up afterwards. So I would say the derivative of this function is equal to the derivative of the outer function, which is e to the power. Leave the power alone, multiplied by the derivative of that power. And the derivative of x squared minus 9 is 2x. This might be nicer to write as 2x e to the x squared minus 9, so there's no confusion about what is being multiplied and what is being raised to a power. Earlier, I mentioned the importance of being able to find derivatives with multiple methods and being able to check that the answers were correct. This is a good example to see that. If I asked you to find the derivative of y equals secant of x, one possibility would be to rewrite it as 1 divided by cosine x, and then using the quotient rule, where the low was cosine and the high was 1. However, another alternative would be to rewrite it as cosine of x to the negative 1 power, different than inverse cosine, of course. So now, this is a composition of functions where the chain rule would be important, because I have my inner function, cosine of x. So that's the one I have to take the derivative of the outer, leave the inner there, and then clean up with the derivative of the inner at the end. So let's see how that would work. dy dx would be the derivative of the outer function. In case it's not clear, the outer function is referring to the negative 1 power. So you think about, you're imagining you're taking the derivative of x to the negative 1 power. The derivative of x to the negative 1 power would be negative 1x, which is leave the inner function there, to the negative 2 power. And now that's all that's left to do is to multiply by the derivative of the inner function to clean up the inner. The derivative of cosine is negative sine. And now I could simplify. Negative 1 times negative sine is sine of x. Cosine squared goes in the denominator. And I have the derivative of secant. Now, most people don't write it as sine over cosine squared. Instead, they write it as 1 over cosine times sine over cosine, also known as secant tan. The derivative of secant x is secant tan. You can memorize it, or you can do it using the quotient rule, or now you can do it using the chain rule. A lot of different possibilities.